Okay, hello everyone. Can you hear me? Yes, you can hear me. Hi, so I'm Lídia del Rio, and I'm your lecturer for quantum physics for non-physicists. So we'll start now, and later on there'll be time for more questions. So let's see how we go about this. So please write in the chat if something is not clear, or if you cannot hear me, or if you cannot understand my handwriting. And I'll tell you later what the protocol will be. So today is the first lecture, and Nuri, can you see the second page already?
Oh, no.
No, it's still the first page, right?
Yes.
Okay, then let's try this again. It's never smooth. Check. Ah, okay, there we go. And if I change page, yes, it works. Very good. Okay, so today we'll talk a little bit about the course outline and motivation for this course. Then I'll tell you a little bit about how it's going to work in the semester. And then we'll start right away with the beginnings of quantum formalism. Okay, so we'll not say much today, but we'll talk about states, give some examples, see what notation we're going to use, and talk about measurements. So first, just a little bit about us. So I'm Lídia, and this is Nuria that you can also see on the Zoom call. And we are both researchers at the Quantum Information Theory group at ETH Zurich. So we're both physicists, and I'm a senior researcher and Nuria is a PhD student. So if you have any questions, so Nuria will be hosting the Zoom meeting, so she'll answer your questions. From next week on, we'll also have another teaching assistant. Good. So why did we decide to create this course? Why quantum physics for non-physicists, and what's the difference between this and traditional quantum physics courses? And what's the overlap with other courses that you might have? Okay. So first of all, I think it's important to learn quantum mechanics, not just for the applications these days to quantum computing, for example, which are very fashionable. And we have other courses that teach just quantum computing, but also to learn the physics itself, because at some level, the world is quantum mechanical, and we want to understand how it works and why it works this way. And there are many, many behaviors that are very different to classical physics, and which are not, they're not all captured by quantum computing, for example. So if you took, for example, a short course on quantum computing, you have some idea about the information processing and what you can do with this kind of physics for in terms of cryptography or programming, but you don't have a good grasp on what effect does this have in the world in general. So that's what we'll be doing here. And now you may ask, well, there are already courses in quantum mechanics and quantum physics at ETH, so why are you creating this quantum physics for non-physicists course? So I will make an analogy, because you might not be physicists, but we are. And what this means mostly is that we'll make lots of metaphors and analogies and comparisons. So imagine that you are watching some people play a card game, which you've never seen before. Okay? And just from their behavior, you try to infer the rules of the game. And this was essentially the situation of physicists in the beginning of the 20th century, right? The game is the experiments that they made, the way nature behaved, and they were just trying to infer the rules. Okay. And if you are in this position, of course, you start by saying, well, this game looks a bit like poker in some ways, but looks a bit like bridge in other ways. And maybe I can take insights from what I learned before and try to infer them to discover the rules of this game. Which is what people did back then. So they started from classical physics and then said, well, but it behaves a little bit different like here. Now it has more of a wave behavior. Now it has more of a particle behavior. Let's try to generalize from these things that we know and find a general behavior, right? And then eventually someone figured out the rules of the game. So at some point, Heisenberg and Schrödinger come up with a quantum formalism, and now we have the rules of quantum mechanics, and then they apply it to all the systems, and they see that it really works. Okay. So how would you go about now explaining someone who's just wants to learn this game, explaining how it works? And the way traditional quantum mechanics courses go about is by retelling the stories, by saying, well, there we were, we made this experiment, this explanation didn't work, then we tried this explanation, it also didn't work, and so on. And then like, this is the formalism that we used for the first 20 years, and then we realized that this formalism now is more useful, but you'll still go through the lectures using the old formalism for a long time. And I don't see this as being very efficient right now. It's one way to learn, but so our way to learn will be to tell you, these are the rules. Now we can watch the game. And then later on, much later, towards the end of the course, we'll try to understand why these rules. Because the history of how we discover the rules do not explain why the game works this way. Okay, why quantum mechanics is this way. And for this, there's a whole area of physics called Foundations of Quantum Mechanics, which is what Nuri and I work on. And we'll try to see later on like other ways to derive, or some ways to derive the rules of quantum mechanics. But for now, I'll just like if I'm explaining to you a new card game, I tell you the rules, you roll with it, and then we'll see how it applies to different physical systems. So what's the overlap here with quantum mechanics 1 and quantum mechanics 2? There's a lot of overlap in terms of content, not so much in terms of methodology. So for example, Dirac notation we'll introduce today, and it's only introduced much later in the quantum mechanics courses. But the types of systems that we'll study, this will be very similar. The overlap with the lecture of quantum information theory, there's a big overlap in approach, and the first few lectures are probably very similar because we need to introduce the basic formalism anyway in both courses. But then in quantum information theory, you'll focus more on the abstract of quantum mechanics and how we can do this to encrypt information, to share secrets, to do teleportation of systems, etc. So this will be much more abstract, whereas we will focus on how nature works. So we'll focus on more concrete systems. And similarly to a course that exists in the next semester, which is quantum information processing. So there, again, the very, very basics, the first 2 lectures will be the same or very similar because we need to introduce the basic formalism, and it's okay if you hear it many times. But later on, they will focus on quantum circuits and quantum algorithms and just this kind of applications, whereas we go through the physics. So I think this course is complementary to both QIT and QIP, and you can take it instead of quantum mechanics. Okay. So that's kind of it for motivation. We'll go over the curriculum a bit later. So let me just tell you some things about the schedule. So we have these lectures on Tuesday and Thursday. And then there's the tutorials with Nuria on Tuesday morning. So at the time of this lecture, but on Tuesday. And there's a tutorial already this week.
Sorry, on Thursday morning.
Oh, sorry, Thursday, yes, not right now. Okay. That's a good opportunity to test that. No. 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 Yeah. On Thursday. So the lectures will be on Zoom, and later on we'll upload it to YouTube. So I don't care particularly if you watch them in real time or if you watch them later at night. that's up to you. We'll try to upload them on the same day. We don't know if this will always be possible. Also, because this is a strange year, there could be maybe for some circumstances, maybe one of us is sick or something, that we might not be able to give the lecture or the tutorial exactly on the day. But in that case, we'll still upload it later, and we'll let you know when this happens. So today Nuri is here, and from next week on, there'll be someone else for the watching the Zoom meetings. So this means that you can ask questions on the chat, and either she'll reply to you by text there, or if it's something that is worth like stopping the class for, then she'll stop the class. But please ask all the questions you have, even if it's like, what's the symbol there? I didn't understand. So we decided to have all the lectures and tutorials on Zoom to protect ourselves mostly and protect you. But we still want to give you the experience of being in a real university and coming to meet us and meet each other. And we talked to the coronavirus team at ETH to try to find a solution. And something we found that works for us is to have open office hours. And what this means is that in the afternoon, on Tuesdays afternoon, starting today from 3 to 5, we'll be outdoors in Hungerberg, outside the alumni lounge. So the link is on Moodle, and you can come and ask questions. So we'll try to do this while the weather is good, so for a couple of weeks, and then we'll adapt accordingly. Okay. So it could be that we need to find an indoors venue, or it could be that we do it only on Zoom from then on, etc. So you can come in person, but of course there'll also be a Zoom room, so you can also ask questions via Zoom. Okay. There's only one electricity plug there, so if you arrive early, you can try to reserve it, and if not, we'll try to bring some extension cords so that you can charge your laptop if need be. Okay. Next thing is the problem sheets, and there'll be a problem sheet every week, and the solutions will be posted the Monday after. And in particular, you're not meant to hand in the solutions, okay? We don't have the testat anymore, which means this doesn't count for your final grade in any way. And you are encouraged, of course, to try to solve them, compare them to the solutions. And then if you still have questions after this, then email Nuria or write to her in the Moodle chat. There's a forum just for questions about exercise, and she'll reply. Yes, that's it for problem sheets, and there's one this week already, as you know. In terms of resources, so I'll upload these notes if I find that they're readable, and I'll also upload written lecture notes, but this might take a bit longer to come. There's also this book by Schumacher and Westmoreland, which is very nicely written, very accessible. We will not follow it exactly, but we'll follow some chapters. And when this happens, I'll let you know. Okay, so not too much today. In terms of evaluation, there's a final written exam in the exam session. Okay. And we'll see in due time if this will be in person or whatnot. Okay, so that's it. Are there questions about the functioning of the course? Okay. Very good. Okay, so then we can start with the rules of the game. So and today I'll give you only a small subset of rules, and we'll see what we can do with them. And then when we're comfortable with this, then I give you more rules, and then we move on. Okay. So today we'll talk about states and measurements, and in two types of systems. So let me just write here what we'll do. How do we represent physical states of systems in quantum theory, and how do we represent measurements? And we'll talk we'll try to talk always about different types of systems. So we'll talk about types of systems, finite dimensional, and infinite dimensional, of which they can be discrete or continuous. So if you do quantum information theory, most of the time you're working with finite systems. If you do more physics, quantum mechanics one, you start with continuous systems, and we'll try to do everything at once because this way you can see the parallels and how to go from one notation to the other. So some examples of this is qubits, spin systems, or polarization degrees. And of a continuous variable could be just the position of a particle. So let's write free particle in space. In discrete could be, for example, the harmonic oscillator, of which we'll see many examples later on in the system, later on in the course. So, sorry, I'm a bit sick. So, let's start with states then. Well, so first of all, we take a physical system, which is a big mess. And inside this physical system, we try to identify a nice, well-behaved subsystem. We'll see some examples in the lectures. So one of the examples that we'll see throughout the course will be trapped ions. Why trapped ions? Because for once, I know it. And second, because it's used for quantum computing. It's a nice example of quantum engineering where you have many different types of systems and interactions, and you try to simplify things as much as possible, such that in the end you can find a system that can be used for quantum information. Okay. So we'll see it also in the exercises every week with a little bit more depth to it. But so the idea is that once you find a quantum system, the rules are that it states act like vectors in a Hilbert space. So let's write here. The state space is a Hilbert space. And what this means is that it's a vector space, complex vector, with an inner product that's well behaved. And so, and what this means is that it's a space of some dimensions with entries in C, okay? So alpha, beta, gamma belong to C, okay? And here this, for example, will be a vector of dimension 3. So we take, for now, we take for granted that spaces, that states are just vectors in a Hilbert space. Okay, later we'll see examples that you'll see how to connect this to physical systems. So let's start with a very simple example. So let's start with the example of a qubit. This means that the dimension is 2, and it's a generalization of a bit. Okay, so states consist only of 2 complex numbers. And now we need to find a nicer way to represent them than just this. So we'll take a basis for the space. So let's take, for example, this basis is called the computational basis. Okay. And then you can write this state. We just expand it in this basis plus beta 0, 1. Okay. And now, because we don't want to write these vectors all the time, we give these names. We call this the vector 0, and we call this the vector 1. And to make sure that they are not just numbers, we'll put something around them. Okay. This is what is called Dirac notation. I'll go into more detail later. And this is what we call a ket. Okay. And it just means it's a column vector. So this means we represent this state as alpha 0 plus beta 1. Okay. And this is the state, for example. So, and this could be the quantum state, for example, of a spin. There's some normalization conditions, which we'll see later. In infinite dimensions, so let's say continuous case, we could take a basis, which we call X, for example. And which is just, sorry. Yes, which is just this, right? So it's an infinite basis with elements in R, and their X is their name. And later on, we'll call this the position, but we don't care about this for now. And then in the same way, we can expand any element, any state in this basis. So we can write that every psi is, for example, if it's continuous in this case, so from minus infinity to plus infinity, some number of X, and then X. Okay, so it's exactly the same here as you did here in this case, right? We could also call this sum over X from 0 to 1, psi of X, X, where this, we just have that psi of 0 is alpha and psi of 1 is beta. Yeah, so it's exactly the same idea. And now this thing here is what we call the wave function. And this thing here we can call, for example, the state, the ket, or the vector state. Okay. So how do we go from one to the other? Because sometimes in physics books, you only see the wave function. You only see this function phi of X. Well, it's very simple. If you look at it, phi of X is just this, where this is the inner product between X and, and the state. Oh. And I will tell you what this means, because we've not seen this object yet. So what is this object? So this is, we take a state and we take the complex conjugate. So complex conjugate. So for example, we have this state psi before in the qubits was alpha beta, which was alpha 0 plus beta 1. And this is the complex conjugate. So it will be a line vector with the complex conjugate transpose. So it's a line vector with the conjugate of the elements. Okay, and this can be written like this, plus beta 1, where 0 is just 1, 0, and 1 is just 0, 1. Okay, is this clear so far? So in this case, what this thing here is, and that's what's nice about Dirac notation. So first of all, this is called a bra. So when they go together, a bra and then a cat, it's called a bracket. And this is what represents the inner product. So the inner product, that is between two vectors, is the same as taking this vector and then this vector, which in our case, if it was alpha, beta, and this was gamma delta, that's a delta, very nice. Then this would be alpha, beta, gamma, delta, yeah, which is alpha star gamma plus beta star delta. So this is a number. This belongs in C. Okay. In the same way, we can have matrices, which will be more important later on. So this should be the opposite. Check, check, which is, so it's a cat bra, and this will be alpha, beta, gamma, delta, and this is now will be a 2x2 matrix, right? With elements where the first element is going to be alpha times gamma plus beta times plus beta times delta star, and so on. Okay, so if we go back to our example, and let's go back to first to the example of the qubit here, right? We take this function and you want to do, we want to find the wave function, okay, using this. So we have psi of x is x psi, and our psi was alpha beta. So psi of 0 is going to be 0 psi. Now there's two ways of doing this. One is to stay in Dirac notation. The other one is to go to the vector notation. So let's do first in Dirac notation. So this will be 0. And here we can write alpha 0 plus beta 1. Okay, so, and the nice thing about everything in quantum mechanics is that everything is linear. So this just becomes 0, 0 times alpha plus 0, 1 times beta. And now the inner product of a vector with itself is 1. So we get alpha. And then a product with a basis vector with another one is 0 because it's an orthonormal basis. So 0. Okay, so that's just alpha. This is one way to do it. Now let's do it in the show it in the vector basis. So first let's start with a new page. And then let's make things a bit more presentable by copying this example. Copying this example. The example. Open everything. Chook, 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 chook. Copy. See if this works. There we go. Almost. Okay, so if we do it in the column basis, in the vector, we go again. Phi of 0 is 0 tac, which is 1, 0 alpha beta, and then this is directly alpha times 1 plus 0 times beta. Okay, so we get to the same result, and in this case it looks much faster to do it directly in the vector form, but in most cases, for more complicated systems, it's actually going to be easier to stay in Dirac notation for as long as possible. Also if you do quantum computing. Okay, so that's why. So you see, what we recovered was precisely these coefficients that corresponded to that correspond to the basis element. So if you do it for the wave function, then what you'll get, we can do this for the wave function so the first example in the continuous case, what we'll do, so now we have psi equals tx psi of x, and if we do x psi, so you get x times this thing, dx psi of x, and everything is linear, so everything goes inside the dx. Oh, everything goes inside the integral q of x. And again, because we chose an orthonormal basis, this is Dirac delta, and then this is just psi of x. Okay. So this is how we go from the wave function to the Dirac notation and back. Okay, so if you're also taking the quantum mechanics one course, you'll see mostly talk of wave functions, and you might wonder how it relates to the states in, for example, quantum information theory, and this is how. Okay. But so far this has been very abstract, so let's look at a concrete example. So another example before we go for a break. And you'll see more examples in the tutorial tomorrow, Thursday. So as I said, a qubit is everything that is just 2 dimensions. And we'll look at normalization conditions a bit later, but for now, no, we'll look at it now. So we have alpha 0 plus beta 1. And these are 2 complex numbers, but they satisfy some rules. So for a reason that we'll find later, the modulo of these coefficients, which are also called the amplitudes, is 1. Okay. Later in the general case, it will be that the sum in x of x squared is 1, or yeah. There you go. Okay. This normalization condition will come around because of measurements, because we'll want the probabilities when we do a measurement to sum up to 1, and we'll explain this later. Don't worry if you don't care about this now. But let's just see how many parameters we have. So we have 2 complex numbers. So that's 4 real numbers. But then we have a normalization. It's going to be -1. And then we'll have a condition that we'll see later. We'll justify later today after the break, which is that there's a global phase that doesn't matter. Okay, so it's going to be even -1. So in the end, we're going to have only two parameters that matter here, which means that we can encode them in the angles, in 2 angles. So there's a very nice way to depict qubits, which doesn't work with more dimensions because it starts having more dimensions than you can visualize, which is the block sphere. And now I think I do like this. Yes. In fact, perfect. So we have 2 real parameters, and we encode them in 2 angles. Okay, so it's going to be, let's suppose a state there. It's going to be an angle psi and an angle phi. And this will be our state psi. So this means that every angle, every state, we can represent on the surface of a sphere, which we call the Bloch sphere. And we put the 0 here, and we put the 1 down here. So let's look at some possible states. We said that these numbers are real numbers, so there's are complex numbers. So there's a state which is just 0 plus 1 over square root of 2 to normalize. Okay, this is what we call the state plus, and this can be 1 over square root of 2, 0 plus 1, which is 1 over square root of 2, 1, 1 in the vector form. And this stays more or less here, depending on the convention you choose for the angles. There's also going to be a state minus, which is 0 minus 1 over square root of 2, which stays here. And there's going to be states also in the other direction. So plus I and somewhere over there. So sorry, this is already drawn this axis. So here plus I, and there it should go to be the minus I, where they got to be just 0 plus values I 1 square root of 2. Okay, so these are some examples of states that we'll see again and again because you can show lots of properties like this. Okay. Now so far we just have states. Or let me give you, sorry, one more example. No, you'll see in the tutorial examples of the continuous case. So we're going to see now how to do measurements. And that's the nice thing about quantum mechanics, is that with these states, for example, psi equals alpha 0 plus beta 1. And you say, wow, you're encoding like here a bunch of real numbers. So in principle, you could encode like a whole encyclopedia into just the state of a small particle. And the short answer is yes, but you cannot read them out. That's one of the strange rules of the game of quantum mechanics. But later on, we'll see, much later in the semester, we'll see that actually this is the only thing that makes sense. Anything else would lead to a very, very strange world and very, very strange behavior. So what happens when we make a measurement? We will see later on what happens physically, but for now I just tell you what the rule is for getting something probabilities and what we actually can measure. Okay. So we start with the simplest one, simplest case, which is a measurement with respect to a basis. And this is a perfect measurement. It's also called a Photon measurement. And in this case, for example, we have a particle and want to measure exactly the exact position. Okay, or we have this qubit and we want to measure in this basis, in the 0, 1 basis, for example. Okay. So we take a basis, let's call it y. And two things, the probability of obtaining outcome y is given by y psi squared. Okay, it's given by the inner product of the basis element with the vector that you're trying to measure. So, for example, so suppose you want to measure the wave function that we saw before, the continuous wave function in the x position, in the x basis. So we want to measure the position of the wave functions of this particle that was y of x. If you want to measure this in, so position means we want to measure in the x basis, what's the probability of getting an outcome x when you measure state psi? So this is x psi, and this is x dx psi of x. And you know where this is going already, because we've seen it before. This is just, square. This is just the module of the wave function. Yes. So this is why the wave function is sometimes called the amplitude, and the amplitude squared gives us the probability of getting the outcome. This is also the reason why we want it to be normalized, because we want the sums of all the probabilities to sum up to 1. Okay. So let's see. Oh, you'll see another example with this wave function in the tutorial, because the interesting thing there is not measuring the position, because I mean, I already expressed the wave function in the position. So it's obviously just this coefficient here. What's interesting is then to try to measure in a different basis. And we'll see this later. So, but let's see the examples with the qubit that we saw before. So with the qubit, we saw that we had this state plus that was 1 over square root of 0 plus 1. And now suppose we want to measure in the computational basis one basis. Okay, and what is the probability of getting outcome plus? Sorry, outcome 0 when you measure the state plus. Well, this is just 0 and our state plus square, and that's 1 over square root of 2 square, and that's 1 over 2. Okay, which will be the same as the probability of getting 1 because they're normalized. It will work in the same way if you try to measure this plus I and minus I states, because of course the modulo square takes care of the complex number. But now let's take a different state. Let's take, for example, psi equals square root of 2 over 3, 0 plus square root of 1 over 3, 1. Okay, and now we want to measure in the same basis. So now the probability of measuring 0 is 0 psi. And we can see that this is square, and this is going to be 2/3 0 0 plus 1/3 0 1. And this one we know it's 1, and this one we know it's nothing, square. So we get this square, which is 2 over 3. But so far we've been measuring always in the same basis. So now let's try to measure it in a different basis. And we'll measure in the basis plus minus. And first of all, we need to prove that this is a basis, right? So is that a basis for the same Hilbert space? And is it a orthonormal basis? And we can say yes, because we need the conditions we need is this to be 1. So the states need to be normalized, but they are normalized by definition. Okay, look. And the other one is that they are orthonormal, so this should be 0, but you can see, we can do it directly, so you can see it's 1 over square root of 2 of 0 plus 1 times 1 over square root of 2, 0 minus 1. Okay, and now we'll get this with this. So you get, how do I make more spaces? Okay, I'll copy this again. Check. So what is this? And we'll do this endlessly in the exercise classes. So 1 over 2, and then we have 0 0 plus, minus 0, 1, minus 1, 0, plus, no, plus, and here minus 1, 1. There you go. Okay. And now that's 0, that's 0, that's 1. This is 1, but because of the sign, they cancel each other, so the whole thing gives 0. Yeah. Okay, so we have a basis, and now we want to measure that state in this basis and know what's the probability. So we want to see the probability of measuring, for example, plus in this state psi. And this is again plus psi. And then you'll do this in the, you'll do this kind of exercise in exercise class. So you have 1 up square, 1 over square root of 2, and here you have 0 plus 1. And now we have the state itself, which was square root of 2 over 3, 0, plus square root of 1 over 3, 1, and square. And it's nice if you try to do it along. So let's take this outside, 1 over square root of 2. Let's take the 3 outside, 2 times. Sorry, let's take 1 over square root of, we take the 2 out, we take the 3 out, so 1 over square root of 6. And now we have here square root of 2, 0, 0, plus 1, 0, 1, plus square root of 2, 1, 0, 0, plus 1, 1, right, square, of which the only 2 terms that survive is this. So we have 1 over 6 square root of 2 plus 1 square. Okay, it's not pretty, but that's the result we get. Okay. And this is the kind of calculations you can do. And as you saw, we can do them both in the discrete case and in the continuous case. We didn't look at the discrete but infinite case, where you just have an infinite sum, but this would be relatively straightforward. Okay. So we'll make a pause now. We'll make a 10-minute break. So let's continue at 10:50. And if you have any questions, you can ask now. Okay. In the meantime, I'll turn off the video. Okay. All right, if we're all back, let's continue. So there's lots of disadvantages to having lectures on Zoom, but on the bright side, you can have a coffee while listening to a lecture, you can exercise, listen to music at the same time. If you watch them on YouTube, you can speed up the volume and watch them in half the time, which I recommend. So I'll take it easy. By the way, someone asked me, we'll post the links to YouTube later once it's actually uploaded. Okay, so I'll send an email around with that, and then there'll be just a playlist and everything will be there. Okay, so let's continue. So we talked about states and probabilities of getting some outcomes in measurements. And there's one very important thing that is still missing, which is what's the state after the measurement. Okay. And in this very simple case, so the principle is, think of a classical experiment, like you throw a die and then you look and see, oh, it's a 3. Okay, and then you look away, and then when you look back, it should still be a 3, right? If it's not a 3, then you find that it's something very, very strange happened. And this is kind of the definition of a measurement in quantum mechanics. It's a thing that you do that if you look twice in a row, you get the same outcome. Okay, so we'll see how this generalizes later on. But in this case, what it means is that if I measure in the basis and I got some outcome, then if I measure again, I should get the same outcome. So the state, for practical purposes for now, will just be exactly what I measured. So post measurement state for now corresponds to the, if I got outcome X, for now it will be, this will be the post measurement state. We will see in a minute how this generalizes in more complicated cases. This is what is called the collapse of the wave function. And we'll see later on in the semester when we learn about interactions between different systems, we'll see how this actually emerges very naturally. Okay, and it's no mystery. So in the examples we saw before, so we had this complicated state here. We had this complicated state over here, and then we measured in the X basis, sorry, in the plus minus basis, which you call the X basis sometimes. And then if we get outcome plus, then the state after the measurement is going to be plus. Okay. For now, we take this as one of the weird rules of the game, and later on we'll see that this is the only rule that makes sense. Okay. So now, how does all of this connect to reality? So let's look at maybe kind of a real life approximation. We think of an electron, and we'll see later the concrete cases. But for now, it's a free electron floating in space, and it has an internal degree of freedom. Which is physicists speak for a variable, which is a qubit, which in the case of the electron is the spin, and then it will have an external degree of freedom, which can be the position, which could be a continuous variable. Okay, so you have, in the same particle, you can have different types of systems. And later on, so on Thursday, we'll see how to combine these different types of systems. But now the idea is that you have, this is not an accurate representation of a qubit, but you have here state 0. Oh, let's make it bigger maybe. You have here state 0 and state 1, or in a different representation, you have here like the little box sphere, where you can only have this simple degree of freedom. But then in addition, you have the whole position on a line of the same particle. Okay, and later on we'll see how to connect these two. And what we did now was see, oh well, we can try to measure this thing, the internal degree of freedom. We can try to measure this thing, but we looked only at very precise measurements. Okay, what's the probability of finding the particle exactly in this position? Now, if you have any sort of engineering or physics background, you know that you can never implement this in practice. Okay, at most, we could do something like asking, what's the probability of being in this interval? Or in this interval here? Or in this interval here? Okay, a much more coarse-grained measurement. And we need to have a way to represent this kind of measurements too. And it's going to be exactly the same. So let's derive this. Okay, so now we want to know if the particle is in this position, so say from x1 to x2. Okay. And the measurement is exactly this. So it's not like we go and measure in every single possible position, but we just have a coarse-grained thing that detects in some way. We'll see later what ways it detects if it's in this interval or that interval or that interval. Okay. So it's not just a measurement with respect to a basis, it's a bit more coarse-grained. And so let's look before at what we had. We had this kind of object, side square. And you can write this. The modulo square is just the thing versus the complex conjugate of the thing. So it's x psi times psi x, right? This is a number. This is going to be a number. Well, in this case, we know what the number is. And this is just the complex conjugate, okay? Now, because these are two numbers, we can change the order and nothing happens. Okay, so we get psi, and now here's the x psi, okay? And now we're going to separate this element here. So let's do this again. Copy. Psi and x psi, okay? And this was if we wanted to measure exactly there. So project exactly there. And now if you have a more coarse-grained measurement, it means that your outcome is not going to be this, but it's going to be something like, so remember that this is now a matrix. And now for coarse-grained measurement, we'll have, for example, particle between x1 and x2. The corresponding matrix is going to be shook from x1 to x2, the x. Okay. So it's going to be the sum of all these elements, each corresponding to an exact position, but now we have over some range. Okay. And the probability that the particle is in this interval x1 to x2 is going to be psi, and now we introduce this thing x1 x2 dx x. And now here comes again psi. Okay, so we just replaced this very precise matrix with this one that's a bit more coarse-grained. Okay, so let's just see first what the result is. Should probably let you do this in the class. So so let's put here dx prime psi of x prime, and this is from minus infinity to plus infinity. And now comes this thing, x1 x2 dx. Oh, I forgot something. I forgot here the x prime. And now here comes again another integral minus infinity plus infinite, dx double prime psi of x, sorry, x prime, double prime, x double prime, okay? And now, oh, it is going to be, sorry, I think I just lost the contact lens. Okay. Okay, never mind. Okay, so we have these three integrals. Let's make one of them light blue. X2, and the other one, and then we have the dx prime, dx, dx prime, and now we have what? Sorry, this should have been x prime, the graph. Okay, good. So now what we have the star of x prime, the wave function of x prime prime, and now we have these two inner products, right? So we have x prime x, x, and x prime prime, okay? And now all of these are going to die unless they are unless for one, so this is, okay, let's just write it down. This is delta x prime x, and this is delta x double prime x. Yeah. So only these terms survive, and we get from x1 to x2 dx of x of x, right? Because the other two integrals go away, and only this survives. Okay. Which is x1, x2, dx of x. That's great. Okay, good. In the other case, in the qubit case, it's hard to talk about a coarse-grained measurement. We'll later see noisy measurements, but coarse-grained, when you have only two options, it's a bit hard to do. Okay, but we can also do this for the discrete case, but just not a qubit. But we'll see later on. So, for example, you could have 2 or 3 qubits, and you only be interested in the parity or on some other coarse-grained variable. Okay. So we did all this. Why? Because there's many ways of representing a measurement, and one of them is a measurement with respect to an observable. And this is just a way of encoding both the probabilities and the outcomes 2 in 1. So a measurement representation via an observable is just taking a matrix that has not only like these basis elements, but also the outcomes. Okay, so this would be, for example, if I want to have the position x, we use this hat to say it's an operator. And this is just the sum, the x of x, which would be the outcome. And then this thing, the matrix element. Okay. So if we do this, we can talk about things like the average outcome, which in this case we call the position, average position, which is represented like this, for example. We'll do this in the class, which is just psi, the thing, psi. Because you see, it's already, what it does is just dx x of the wave function, and here comes the probability of getting one specific position, and then you average over all the you average with the value of the outcome. Okay, but there's nothing fundamental about this. These labels, you could multiply them by 10, for example, and it still represents the same physical interaction. It's just really a label. Okay, so this is just a label. It's a label. And when you learn quantum mechanics 1, you learn essentially from the beginning just these observables. Okay, and it's important to understand what they are. So they are the matrix elements. This represents what's actually being measured. So the physics, the physical interaction. So this will be the physics. For example, the basis with respect to which it's measured. And this is just a label that we give to the outcome. Okay. So another way to represent measurements is via projectors. And this is again for cases like this coarse-grained that we saw. Later on, there'll be more complicated ones. It's just getting rid of the labels and just say what are the possible outcomes. Okay, so sorry. This I say, for example, that the measurement corresponds to outcome 0, outcome 1, outcome 2. And these things here are projectors, which means that px squared is the same as px. I'll give you an example in a second. And the sum of all the px should be the identity. This is the identity matrix. So, for example, in the case before, in this coarse-grained case, for example, you could think of these three of, let's say, 3 projectors. Of 3 projectors. One which just sees if it's between x1 and x2. So this is our P1. One which just sees from if it's smaller than x1, and one that just says if it's larger than x2. So this is P0 and this is P2. Okay. I'll give you, let's do the example here. So in this example, we have P0 is just the sum from -infinity to x1 of dx x. P1 is the sum from x1 to x2 dx x. And P2 is the sum from x2 to plus infinity dx xx. Okay. Are these projectors? We can see what happens. Well, if you sum them all, you see that. Okay, let's see. Are these projectors? First of all, if I sum, let's do it one by one. So P0 plus P1 plus P2 is just a sum from minus infinity to plus infinity of x, x, dx. And this is precisely the identity. You'll see an exercise in the exercise sheet of this. Because if you apply this operator on anything, it doesn't change it. And we can do, for example, what P0 squared is. And that's, so let's say minus infinity x1 dx x times minus infinity to x, sorry, to x1, x1, and here dx prime, x prime, x prime. So this gives you the two integrals, both to x1 of dx tech, and then you get what? X, and now these two multiply in an inner product, check, check. And this is again, this delta xx tech. So all that survives is this, 2x, x, which is P0. By the way, this is as much integrals as we'll do. And this is the only way we reach integrals into the course, really. So, so now we have this measurement, which is P0, P1, P2, corresponds to 3 outcomes. We saw what the probability of getting P1, for example, was. This is what we saw before. And now we can ask what's the post-measurement state? Okay. And what's the rule again? If you measure again, is to get the same outcome. Okay, but it does not need to collapse to a specific position. It just needs to stay within this region. So this is a slightly generalization of what we saw before of the post-measurement state. And we'll see later on other examples. So in this case, it's just going to be the projector x if we got outcome x times the wave function. Okay. So for example, if we got outcome 1, this meant that the particle was inside this box. Okay. From x1 to x2, and the post-measurement state is going to be divided by the probability. Divided by probability. Because we need to normalize it again. That's the only thing. So if you got outcome 1, we get what? 1 over the probability, and we'll don't care about this for now because we don't want to compute it, times px, not p1 psi, and this was, let's just call this whole thing gamma. Okay, it's going to be gamma, and now the px, which was px xx from x1 to x2, and now here comes the psi, which is dx prime phi of x prime x prime, and here you have to believe me there's another x prime. Okay, minus infinity plus infinity, and this is going to be gamma, the two integrals, psi of x prime, and now x prime, and it looks like a mess, but what's important is that this is a complex number, and we know that it's just a delta x prime, And this is a cat, so it's a column vector, and this is a bra, so it's a row vector. Okay. So only these terms survive, which means that we have gamma, and the integral goes only from x1 to x2, psi of x prime, sorry, psi of x, x, dx. Okay. And again, sorry, x. Sorry, x. This was not that. Sorry, I was running ahead and doing the case of when we have density matrices, but don't worry about this for now. Okay, so we get this. So what we got is a renormalized wave function. So renormalized by this factor here, which was just the probability of that it was inside this box. But otherwise, the wave function is the same. So let's try to represent the before and after. Okay. So here's x. And here, I'm not very good at representing complex numbers in 1D, but let's put here the amplitude of the wave function. And here we have this x1, x2. And this was the state before. Could be something, could be, I don't know. We don't know what it was, right? For example. Okay. And then, so this is just, we're just representing this function, okay? And because this is a complex number, we just take the modulus, so it's a real number, and I can put it in a line, in an axis, okay? So we measured with a measurement that just asks, is it on the left, or is it in the middle between these 2 points, or is it on the right? And because of luck, we got the response that it's on the right. Okay, and the wave function, the state after the measurement, the only condition is that if we measure it again, it should be again in the middle, but otherwise it doesn't change much. So what we get is a state that is just kind of an amplified version of this. Something like this. Okay, so this is the post-measurement state, or at least the amplitudes. But if we measure it again, it should not be on the outside. We will later see why this is the reason. The spoiler is that a measurement in the end is going to be a physical process in which our measurement instruments will interact with the thing we're measuring, and then photons will go from this measurement instruments into our eyes. And what we're doing when we measure is just to correlate ourselves with the system that we're measuring. Okay? And because this measurement was very coarse-grained, the correlations are kind of weak. So the only thing that's correlated is whether it's inside the box or outside, and otherwise we do not disturb the state that much. If this does not make sense now, don't worry, it will make sense in a few weeks. Okay. So that's it. And I'll do now only one more thing before we go, which is see what this looks like in the block sphere, although we'll do this in the exercise class. So this is another example. In the example of the qubit, let me do. We saw, for example, we had some state that was something like this. So it was square root of 2/3, 0 plus 1/3, 1. And so here is state 0, Down here, state 1. And here, state plus and minus. I think it might be the other way around. So the plus and minus really depends on the convention for the for the angles. And what I want to tell you, which is the reason why we use the block sphere at all, is that the probability of this is related to the cosinus of this angle here, okay, of this angle alpha between the state that we're measuring and the basis element corresponding to the outcome. Okay, and the post-measurement state, in the case of the qubit with this measurement, is going to be this. It's going to be there. Positive, measure plus. If it got on the outcome minus, then the rule again is that if you measure it again, it should get the same outcome. So then it should be minus. Okay. So let's just recap everything we did today. Okay. So the states, of which I have not given many physical examples, they correspond to cats, which is the same as vectors in a Hilbert space. And we saw the discrete case. Discrete case, we can represent them as column vectors. In the continuous case, we just set these integrals with the wave function, okay? The reason why it's called wave function is again for historical reasons, and we'll see this later on. Okay? And of course, the discrete case also has a wave function, but normally we don't call it that. Okay, that's just convention. Good. Then we saw that when you do a measurement, the probability is given by some sort of inner product. And we saw this with respect to a basis measurement. And then we saw the coarse-grained case. And we also found this way of representing, which is with respect to an observable. And we saw that the coarse-grained cases, we do it as projectors. Okay. And finally, we saw the post-measurement state. Okay. So what is missing here to do physics is two things. And this is what we'll do next time. So Thursday, we'll see how states evolve. So, and we'll see how to compose several systems. Okay, and that's when things will get complicated. So first, it's important that you do the tutorial and do really the exercise to make sure that you're comfortable with this. Once we have the evolution and composing several systems, then we can talk about what the measurement means and how we implement the measurement physically. Okay. Then later on, we'll do examples of having problems in one dimension. Much later on, we'll do examples of having problems in 3 dimensions. And we'll also develop the abstract part, so the theory part, which will be, well, these were very simple states where we have, in a way, perfect information about the state. And how do we model lack of information about this? And how can we use this to model physical systems? And then we'll see a very nice example, which will be thermodynamics of quantum systems, and how to make the smallest possible heat engines. And this is something we can do in a couple of weeks from now. So hang on, I know that today was mostly a lot of theory, but hopefully you have already like the basics to start relating things that you might have seen in quantum physics lectures with things that are common, for example, in quantum algorithms. Okay, we have ways of translating from one language to the other. So we did cut the break a bit short, so we'll end now. And if you want, you can come this afternoon to meet us outside the alumni lounge. And if not, then you'll see Nuria on Thursday morning, and then you'll see me in the afternoon. Okay, and I'll send links to YouTube later today. Ciao.